Good afternoon. It's time to get started. So first announcement, I already graded the exams. I'm still working on putting the comments and the points in the Canvas site. So we'll be posting everything by Wednesday, hopefully. And then on Wednesday, we're gonna go over the questions and discuss the exam. So that will happen on Wednesday. So far, performance was better than the first exam. There's still a couple of students that are not doing as well as I was expecting, but most of you did very well. So that's good news. But we'll go over the details on Wednesday. Today, we're gonna start a new lecture. This is connected to what we discussed, the lecture on material handling before the exam, before the second exam. So just to give you a quick review, we discussed different type of material handling equipment. And among them, we had the transportation equipment, which includes the conveyors, the cranes, the industrial trucks, or no equipment. We also have the positioning equipment, unit load formation equipment, storage equipment, identification and control. So we went over that list. We discussed different types, what are the advantages and disadvantages. This material was not part of the second exam. This material for the third one, and the last exam for the semester. Third exam of the semester, remember, final is optional, so keep that in mind. So if you do well on the first 3 exams, then you can decide whether or not you want to take the final. So going back to this, so today we're gonna explore a bit more on transportation equipment. Specifically, we're gonna talk about conveyors, and we are gonna talk about a specific type of conveyors and how to design those based on the requirements from your system. So that's what we're gonna be doing today. So lecture 10 is on conveyor models. So we had 2 parts for this lecture. Part 1 we're going to cover today, and then on Wednesday we're going to discuss part 2. Part 1, before we get into the details, this is linked to our first objective for this course. So these are the things that you're supposed to learn by the end of the semester. So developing an understanding of principles of facilities location, layout, and material handling systems. And how that connects to facilities design. So the agenda for this afternoon, we're going to talk about trolleys and similar conveyors with discrete carriers. And what that means is we are going to design, or I'm going to teach you how to design for a conveyor that has a carrier and can only have certain number of items in it, and it moves around a loop. And each location and within the loop, you have different stations, and you are able to load this carrier, and you can unload that carrier in each one of these stations. So designing for the capacity for these carriers based on the number of stations that you have in your area. And this is assuming what we call a deterministic loading and unloading sequence. So anybody knows the difference between deterministic and stochastic? So when we say deterministic, what does that mean? Anybody remember the difference between deterministic and stochastic? Okay, so if you're an industrial engineer, you take a class IE 3340 that is called deterministic operation research, and then you take another class that is called stochastic operation research. So there's a difference between those two. In a deterministic problem, we assume that we know with certainty what are the parameters. So for example, if you're thinking about a scheduling problem for a production system in which you are trying to decide how many units you're going to produce in the next week, you assume that you know with certainty how many units are going to be needed next week, which is typically not true, right? The only thing you can have is an estimate. You don't know what's going to happen next week, but you make the assumption that you know that for certain. And that's what we do in deterministic problems. We assume that we have all the information, and that information is not going to change. In stochastic, we take into account uncertainty. So what that means is, instead of saying next week I'm going to need this many units, 100 units, we're going to use the probabilities to say there's a 10% chance that I'm going to need 100, there's a 50% chance that I'm going to need 120, and there's a 40% chance that I'm going to need 90. And then we do the planning based on those estimates and those chances. So that's the difference. So what we're going to do today, we're going to focus first on the deterministic scenario, and then on the next lecture, we're going to look at the stochastic scenario in which we consider the Poisson arrivals. Okay, so hopefully you got the difference. It's very important not only for the academic world, but also when you go outside. You'll see most of the models that you will see in practice, most of them assume that you're using deterministic information. Problem is, most of the time, those decisions that you're going to be doing based on deterministic information are not going to be good decisions. So that's why if you can add this uncertainty, you can forecast and give that value. We're able to compute that variability in what can happen in the future, and you'll be able to make better decisions. So hopefully that makes sense. So what we're going to do today, these are the learning objectives. We're going to learn models for specific type of conveyors, and we're going to understand basic procedures for calculating horsepower requirement for power belt and roller conveyors. So as an introduction, so again, we're going to be focusing on the conveyor type of material handling equipment. These are fixed pad material handling systems that are among the most widely used material handling systems. And they include material handling equipment such as power belt and roller conveyors, trolley conveyors, or similar conveyors like the ones that we saw in the previous lecture. And those can be also automated guided vehicles. So again, you're carrying these products from point A to point B. Those can be transported using this power belt or roller conveyors. Could be trolley conveyor in which you have specific capacity for the carriers, or you can have these automated guided vehicles that are used frequently in these large warehouses where you put together orders for the customers. So the models we present in this particular lecture provide some basic procedures for designing or analysis of various type of conveyors or material handling systems that have a fixed path. If you remember our previous lecture, we discussed the difference between the cranes, the trucks, or the fire trucks, and also the conveyors. So for the conveyors, we have a fixed path. And these are mostly justified if you have a high volume of units that you need to move from point A to point B frequently. So you see those, for example, in these warehouses where you are putting together shipments, or you're like you have a storage and then you have to put the shipments together for transportation. And these are the other type of conveyors, the rollers. So going back to our focus in this lecture, we're going to focus on the trolley and similar conveyors with discrete carriers. So these are the type of conveyors, the ones that are shown in this picture. So you have a specific capacity for each one of these trolleys. And the idea is knowing the stations that are located around these trolleys, knowing the amount of loading and unloading that you have to perform. There's another type. Designed for the capacity of these trolleys. So how big are these trolleys for your particular scenario? So we present two types of models for conveyors with discrete carriers, such as the trolley conveyors. First, we're going to focus on the deterministic model. That's what we're going to do today. And then we're going to focus on the analysis of closed loop unidirectional recirculating conveyors, in which we have this discrete meaning that you have a specific capacity for the carriers. So why we need this type of models? This was developed because of a number of operating problems that occur with trolley conveyors. For example, at a loading station, no empty carriers were available when a loading operation was to be performed. So if you don't have a good design, your trolleys don't have enough capacity, and you face the problem that if you need to load an item, you might not have enough space, or you might find all the trolleys full at some point. So that becomes a problem. Now you're holding some of the units in your station, and that's creating some delays in the process. So that's one of the problems. And also, an unloading station, no loaded carriers were available when an unloading operation was to be performed. So let's say this is the opposite scenario. You had to pull one of these items in order to continue the process, but you cannot find a loaded carrier to do the unloading. So those are typical problems if a good design is not in place. So conveyors provide many of the links among workstations. So if you go to a facility, a production facility, most likely at some point you will see a conveyor that is moving product from point A to point B. So those are the links between the workstations or work areas in modern production and distribution systems. Some conveyors are used basically as a transport system. So again, they are not adding anything to the product. They're just there to move items from point A to point B. Some of them are used to storage, for storage or accumulation process. So you're holding, this is, yes, you're holding product in this space until more space is available in the other area, or you're just using to split them as a way to know where each product needs to go. So storage or accumulation purposes, where others support both transport and storage functions. As I mentioned, some of them are called sortation conveyors that are used extensively by companies that move parcel packages and also mail. So they have multiple functions. Most of them are used for transportation purposes, but again, some of them will serve also as a storage area. So what is involved in a conveyor system? You have the conveyor equipment, the loading and unloading stations. So for sure, most of the time what you're gonna have is a conveyor. At the beginning, you're loading, at the end, you're gonna unload. But that's not the only scenario, right? You can have some unloading and loading happening in between. So you have the conveyor equipment, you have the loading and unloading stations, the operating discipline or computer control employed. So if this is going to rotate in one direction, it's going to rotate in the other direction, how fast would this conveyor will move? Those are the questions. System design parameters include equipment parameters, such as the speed of the conveyor, waiting space allowances for incoming and outgoing loads, and the number, spacing, and sequencing of loading and unloading stations around the conveyor. So going back to the difference between discrete and stochastic, and most of the, I mean, I'm talking to mostly IE because that's where most of my coursework is. When you're building these simulation models to study a system, basically what you're building is stochastic model, right? So you're using a simulation, you're considering the uncertainty in these areas, and you're trying to make decisions by considering the stochasticity of the system. So those areas that are listed here in this slide, we can assume to be deterministic, right? And we can solve the problem mathematically, probably. But if you have a stochastic, for example, loading and unloading, that right there is just adding a complication, a challenge to your design. So as an engineer, you have different tools that you can use to address those issues. So the principles to be used in designing closed loop. So we're going back to this particular example of conveyor systems, the closed loop unidirectional conveyors. So what are the principles to be used? We're going to have the uniformity principle, which says the material should be uniformly distributed over the conveyor, right? So you're not going to have a bunch of them moving as a mountain around the conveyor. Separate them, which is typical. Capacity principle, the carrying capacity of the conveyor must be greater than or equal to the system throughput requirements. Okay, so they have at least to have that type of capacity equal to the throughput required for the system. So if you're requiring a throughput of 100 units per hour, conveyor should be able to have a capacity at least at that level. And the speed principle, the speed of the conveyor, which is measured in numbers of carriers passing by a fixed point per unit time, must be within the permissible range defined by an unloading station requirements and the technological capabilities of the conveyor. So again, if you're requiring a speed that is not possible by the technology that you have available, then you might need to switch the equipment. So everything has to be within these bounds. Any questions so far? Okay, so let's look at some math. Okay, so that's what we wanna talk now about the design and what are the things that we are going to be considering when making these computations. So conveyor loop with deterministic loading and unloading sequences. So this is the scenario that we are going to study. As you can see here at the top, we have a loop. The loop is representing the path for the conveyors. And those dots, black dots right there, are representing the carriers. So what we have here is the discretely spaced carriers. So we are assuming that they have been spaced have the same distance between them. And then around this path, this conveyor path is moving counterclockwise in this case, you have some stations, right? So station 1, 2, 3, 4, 5, up to X. So you have particular numbers, specific number of stations that you're going to have placed around the conveyor. So there are S stations, as I mentioned. S is the parameter. You can see that here. Located around the conveyor, number in reverse sequence to the rotation of the conveyor. So you can see the conveyor right now, or in this example, is rotating in this direction, and the numbers for the station are going opposite to that direction. So we are numbering clockwise in this case. Each station can perform loading and unloading. Okay, so for example, station 1, you can place some items in this carrier, but you can also remove items from that carrier. And that happens for every single station. So each station can perform loading and unloading. There are K carriers equally spaced around the conveyor. So we are going to use K to denote the number of carriers. And S is the station number. So an important note here is the passage of a carrier by a workstation establishes the increment of time used to define the material loading and unloading sequences. So if we fix, let's say we are going to focus on station 1, this carrier will move through this fixed path, and at some point it's going to go back to, or going to meet this station 1 again. So we're going to use that time. It takes that carrier to move around until it reaches this point again to compute the increment of time. And you'll see how that works in a minute. But for now, the parameters that we have defined are K, number of carrier, S is station number. So as I mentioned, we're going to use the location of one of those stations as a reference point to define the time. So in our case, we're going to use station 1, which is this station right here, to define our, so station 1, it could be any of them. So I chose 1 just because it's easier to remember. It's used as a reference point. And consequently, carrier N becomes carrier N plus K immediately after passing station 1. Okay, so after passing this reference point 1 time, then you're gonna know that you have passed that station these many units of time. The sequence of point in time at which a carrier passes station 1 is denoted as Tn. Okay, so Tn, where Tn is the time at which carrier N passes station 1. The amount of material or number of items loaded on carrier N as it passes station I is given by this function, Fi of N. Okay, so Fi of N is going to keep track of the amount of material or number of items loaded on carrier N as it passes station I. The amount of material carried by a carrier N immediately after passing station I is going to be denoted by this other parameter. So Fi is the number of items being loaded, and then the amount of material after that loading has happened is H, or capital HIN. And we know that each carrier may hold multiple items. Okay, so we are defining all these parameters. You'll see how this works in a minute. But the idea again is to knowing these loading and unloading sequences, knowing how many stations you have, how many conveyors, and you have 1 conveyor, but how many carriers you have, define the capacity that you should have for each one of these carriers. So for steady state operation, the total amount of material loaded on the conveyor must equal the total amount of material unloaded. So this is just basic definition of flow. Everything goes in, then the only thing you can get out of the system is what goes in. So that's the flow also associated with this system. Since it is assumed that the conveyor will be operated over an infinite period of time, the sequences FIN are assumed to be periodic, and we're going to define also the period for that. So we're going to have P defining the period. Thus, we'll know that, as we define here, amount of material loaded on carrier N as it passes station I will be given by this, and that will be equal to that amount, which is N plus the period. Additionally, we're going to have again, the flow definition. So the amount that goes in goes out. So that should be equal to 0. Because of the requirement that all material loaded on the conveyor must be unloaded. So everything that's loaded into the conveyor will be unloaded at some point. So the summation of the positive loading, positive unloading, negative, summation of all of them should be equal to 0. So in analyzing the conveyor, it is convenient to employ the following equation. So now we have capital F1 of N that says that that's going to be equal to the summation of everything that's loaded into from I to S. So from station I equals 1 until station S of Fi of N. Okay, so we have multiple things we have defined so far. So let's try to make sense of all this. But before you get into the actual computations, we can state some of the results of these mathematical definitions. So first, so remember this is an iterative process. So at some point you're going to load in one station, then the other point you're going to be unloading, loading, and that's going to happen at different stations throughout the time that you're observing the system. So following those assumptions, we had the following results. So if we want to reach a system that reaches steady state operation, we need to make sure that this K over P cannot be an integer. So if we want to reach that steady state operation. So again, K is the number of carriers and P is the period. Okay, so that mathematical operation K over P cannot be an integer in order for the system to reach the steady state. And then we're going to let R is defining the reminder of K mod P. R over P must be a proper fraction. So the top number less than its bottom number for general sequences of F1 of N to be accommodated. So we're going to check also on that. And it's also desirable for P to be a prime number. So for this mathematical process to work, we need to make sure that these conditions are satisfied. We don't have an integer for K over P. R will be equal to K mod P, and R over P must be a proper fraction, and P must be a prime number, or the period must be a prime number. So if you don't know what the operator R equals K mod P means, R is given by the remainder following the division of K by P. So for example, if we have 12 mod 7, what this means is that this is equal to 5. So if you divide 12 by 7, the remainder will be 5. So this operation, what is doing is finding the number, that remainder for the division. Same thing for 26 mod 8. So if you do 26 divided by 8, the remainder of that operation should be 2, right? Because 8 times 3 is 24. So you're going to have 2 as the remainder of that operation. Okay, so using this, now we can get into an example. So I have those operations there. So the materials balance equation for carrier N can be given as follows. So we're gonna have these material balance equation. Remember HI, H1 is the amount of material carried by the carrier N immediately after passing station I. Okay, so that's gonna be given by this equation. H of 1 of N equals H1 of N minus R plus F of 1 of N. And in order to determine the values of Hi of N, the following approach is taken. Okay, so we are going to go through the process of finding these expressions for H of 1 for each one of the stations. So we are gonna, in order to determine the values of H of I of N, the following approach is taken. We're gonna define H1 star of N be a particular solution to equation 1 and use the recursion H1 star of N equal to H1 star of 1, N minus R equals, plus F of 1 of N. And we're gonna solve this assuming that this first value for HI is gonna be equal to 0. Okay, so we make sure that we are keeping track of these parameters. So K is the number of carriers. S is this number of stations. Or the number of the station. And we are going to use I to denote the stations, right? So I is used as to identify the station. N is used to identify the carrier. Okay, so we are going to formulate this. We want to know what's the, let's go back here, HI of N, right? So we want to know what's the amount of material carried by carrier N immediately after passing station I. Okay, so in this first equation right here, we're looking at station 1, and we want to know how many items are being what is the amount of items that are in carrier N after passing station 1? And we're going to use that equation to find that number. So in order for us to start computing these numbers, we have to start somewhere. And most of the time when you have this iterative process, you start by assuming that your first value is 0. Okay, because you start with an empty system. So that's what we are doing here. We are assuming that we start with an empty system and then the loading and unloading is going to start happening. So after passing station 1, carrier 1 has a capacity of 0. Or I'm sorry, not capacity, but an amount of material equal to 0. And then assuming that we start with the empty system, we can start computing the rest of them. Okay, so that's what we're going to start doing now. So A star of H plus 1, I plus 1. So again, I is the station. So at station 2, if we start with 1, 1 plus 1 is 2. How many items after passing station 2 you have in carrier N? And that will be equal to this difference. So after we compute all the H star 1 I values, we can also find out what C is. C is going to be the minimum H star of I of N. And then using that parameter C, we're going to compute the values for HI without the star And then B, which is the required capacity per carrier, is going to be equal to the maximum of all the values that we have found for each. Okay, so it's an iterative process. We're going to first find all the HI star values. Then using that information, we're going to find the minimum. The minimum is going to give us this parameter C. And then with C, we're going to find the HI without the star. And those HI values are the ones that are going to tell us, okay, these are the maximum amount of material that we saw in these carriers after going through all these periods. So we should design our conveyor based on that maximum amount. So whatever you found to be the amount of material that was at the highest at any point where the system was steady state, that should be the capacity of the carriers for your system. So you are able to accommodate that capacity in your system. So let's look at an example. Okay, so here we have, to illustrate the deterministic solution procedure, we consider a situation involving a single loading station and a single unloading station. So we only have two stations. So this is a very basic problem. Only two stations. And a conveyor with multiple carriers moving around. You have a loading and unloading station, as we see in this figure. The conveyor has 9 carriers, equal spaces, and determine the required capacity per carrier. That's what we're going to find in this problem. And the loading and unloading sequences occur at a period of P equals 7 and are given here. So F1 is the sequence of loadings that are going to happen here per time period. So you're going to load one first, then another one, then 2 on the next carrier, 2 on the next carrier, 2 on the next carrier, 1 in the next carrier, and 1 in the next carrier. So we're looking at the deterministic scenario, a deterministic scenario in which we know what's going to happen, right? So I'm giving you that. This is what we expect to happen per time for loading. And then for unloading, we are not going to load anything until we get to this period right here in which we're going to unload 5 and then we're going to unload 5. So this is the sequence of loading and unloading that are going to happen in this example. And we're going to use that to determine what will be the maximum capacity that we need for our conveyors. So for our carriers in the conveyor. So let's start by finding F1 of n. So if we remember, here, we are going to look at each station. I'm sorry, we're going to do the summation from I equals 1 to S of F1 n. So essentially, we are going to look at each one of these items, and we're going to do the F1 plus F2. And for the first one, that's going to be equal to 1. 1 plus 0 is 1. 2 plus 0 is 2. 2 plus 0 is 2. Then we have 2 plus 0 is also 2. And then we have 1 plus minus 5, that's minus 4. And then minus 4 again. That's F1 of n. And then we are gonna look at also computing the R. So R is gonna be K mod P, and this is gonna be period is 7, and we have how many? I'm sorry, we have 7 carriers. No, we have P equals 7 and 9 carriers. So this is 9 mod 7. So that's equal to 2. So note that K over P is equal to 9 over 7 is not an integer, and R over P is 2 over 7, which is a proper fraction, and P7 is a prime number. So we have satisfied these results. We want to make sure that those are satisfied before we proceed. And those were satisfied based on our computations. So now we move forward. So recall the amount of material carried by carrier N after passing station I. Is denoted by H of I of N. And as we stated, since we're studying our system, or we are assuming that we're starting with an empty system, we're going to assume that the first one, H I of star of 1, is going to be equal to 0. And we're going to employ the relationship H star of 1 of N is going to be equal to this expression right here in yellow. So we're going to determine H1 star of 3 as follows. So so you have to go back here. You noted R as 2, right? We found that R equals 2. And so the next, so if you look at this expression right here, and you know that this R is equal to 2, the value that we have right now to solve this problem is HI star of 1 equals 0. And we want to use that value here in order to solve for the next one. We know that R equals 2. So what will be the value of N if we want to make N minus 2 equal 1? 3, right? So the next value that we can compute using this amount that we assume the system to start empty in station 1, the next value that we can compute using that value, because remember this is an iterative process, so we start with 1, and then we are going to look at station 3 and the status of 3, because we know that 3 minus 2 equals 1, and that's the value that we can compute at this point. So H1 star of N equals 3 will be equal to H1 star of 1 plus F1 of N equals 3. Right, so we know we are assuming that station 1 we're going to start empty, so we need to use this value to compute the rest of the H values. Okay, so what is the next value that I can use? Well, I need to look at this expression. I know that R equals 2. So in order for this to be equal to 1, which is the value that I have, I need to look at station 3, because 3 minus 2 is equal to 1. And now I can substitute that into this expression and find the next one, which will be for n equals 3. Okay, so A star of 1 for n equals 3 will be equal to this value, which I know, plus this value that I computed in the previous slide. So I can use f1 of 3, and I can use this value to compute this sequence. So that, let me use a different color here. So H1 is this number. So this is 0 plus this value is going to come from here, which is f of 1 of 3. So this is going to be equal to 2. And this is equal to 2. So H1 star of 3 equals 2. So I now have H1 star of 0 and H1 star of 3. I can use H1 star of 3 to compute the next one. Okay, so let's do that. So following the same strategy, so we have we have this one. That's the one that we computed in the previous slide. H1 star of 3 equals H1 star of 1 plus F1 of 3, and this equal to 0 plus 2, which is equal to 2. So likewise, I go back to this expression, right? So I now have H1 star of 3. So can you tell me what's the next number that I can compute based on this? I'm sorry. Wanted the highlighter. So I'm gonna need to look at this again. I know the value of R is 2. R is not gonna change. So I have H1 star of n minus 2. And I want that difference. Yes, that's correct. I want this difference to be equal to 3. Right, so for this to be true, I need n equals 5, correct. So likewise, I'm going to compute H1 star of 5, and I'm going to use this value, right? So this will be H1 star of 3, because 5 minus 2 is 3, plus F1 of 5. So H1 star of 3, I know that value, this is 2. And now I have to go back to F to find the value of F1 of 5. So this was 3 or 5, that will be 2. So this is 2 plus 2, and this is 4. So I now have H1 star of 5 The next one, you know, we are adding 2, right? So we started with 1, we went to 3, we went to 5. So the next one will be H1 start of 7. So H1 start of 7 be equal to H1 star of 5 plus F of 1 of 7. So I know the value of this is right here, 4. So this is 4 plus F of 1, 7. So this is 5, this is 7. So this will be minus 4. So this will be 0. Okay, so next will be H1 star of 9. However, since our period equals 7, we cannot get to 9. So we are basically restarting the count. So 7 is the size of the period, right? So P equals 7. So we need to add 2 now. Instead of going to 9, we're going to start from 0. So it's going to be 1 and 2. So we are now going to compute H1 start of 2. So since P equals 7, H1 start of 9 will be equal to H1 start of 2. And we are going to compute that. And you will see how this accounts for every single piece that is missing. So we have 1, 3, 5, and 7. Now we're going to do 2, 4, and 6. So H1 star of 7. I'm sorry, this should be 2. Let me erase this. Let me change the color too, because this. So H1 star of 2. So let's say our period was 9 instead of 7. So in that case, you will compute H1 start of 9, right? But in our case, the period is completed after 7. So we have to go back to 2 to restart the count. So you go to 9, instead of going to 9, 7 is the last one, so you go 1, 2. So H1 start of 2 will be equal to H1 star of 7 plus F of 1 of 2. So this is 0. So we got 0 here. And then we are going to look at the value of the second period here. That will be 1 and 2. So that will be this one right here. So it's 0 plus 1. This equal to 1. So I have 2 plus 2 is going to be 4. So now I'm going to compute 4. Follow the same process. H1 star of 4 will be equal to H1 star of 2 plus F1 of 4. So this will be 1 plus F of 4. Going back here, that will be 1, 2, 3, 4. So it's 2. So this equals to 3. And then the last one, 4 plus 2 is 6. That's the last one. We have computed the rest. So H1 star of 6 will be equal to H1 star of 4 plus F of 1 of 6. This will be equal to 3 because of this plus 6 here. That'll be 1, 2, 3, 4, 5, 6 minus 4. And this will be equal to minus 1. Okay. So I now have all the values for the H stars. Remember the next step. Now knowing these values, I can compute C. Okay, so I'm going to look at each value of HI star. That's step 3. I'm going to find the minimum, and I'm going to name that minimum C. But before we get into C, missing one thing here. Oh yes, I'm skipping one step here. So we found the values for H1. Okay, we found the values for H1 star. That's for the first station. I cannot go and compute C yet because I have to find the H values also for the next station. In this case, we have 2 stations, so I have to find it for station 2. So I have to go here in order to find H star of I plus 1. I have to use the values of H1 and subtract them by the value of R. So let's do that before we get into step 3. So that's what we are stating here. So let's put the H1 star values at the top. So we have H1 star of n equals this set of numbers. We have 0, of 1, 2, 3, 4, minus 1, and 0. And those are in order of n, right? So H1 star of 7 is the last one is 0. Okay, we found them in a different order, but you had to sequence them based on the n value. So we have that. Now we can compute the value for the other station. So H1 2 star of n be equal to values of H1 star n, which are again 0, 1, 2, 3, 4, minus 1, and 0, minus the F values. So the F values of 1 are here. So that's what I'm going to subtract now. So this is minus 1, 1, 2, 2, 2, 1, and 1. So H star of 2 of n equals 0 minus 1 is minus 1. 1 minus 1 is 0. Then we have 0 again. 1, 2, minus 2, and minus 1.
So 0 minus 1 is minus 1. 1 minus 1 is 0. 2 minus 2 is 0. 3 minus 2 is 1. 4 minus 2 is 2. 4 minus 2 is 2. Minus 1 is minus 2. And 0 minus 1 is minus 1. Okay, so now we have all the values for H1 star and H2 star. If you have more than one station, more than two stations, in this example, we only have two, right? Two stations, one here and one here. If you have three stations, then you have to go and do the same thing again for station 3. Yes. You're referring to these values? So where are you referring to? Here? Yeah. Oh, so why don't we use this instead of? Yeah, so going back to the description here. So everything is going back to FI. Okay, so yes, what we computed was capital F. Yes, yes. So we use the values that we observed for H1 for HI star, and we subtract that by the F of 1, in this case, F of I of n. So we are computing for I plus 1. In our case, I plus 1 is 2. We use the values for 1, and they have values for 1. Good question. So now we can get to this part in which we're going to look for the minimum of all the H values, including station 1 and station 2. So the minimum for all those H values, we have to observe these numbers right here. And these numbers right here. And find the minimum. So in this case, I think that minimum is how much? What is the minimum value between those two sets? -2. So that'll be this guy right here. Okay, so C C is going to be equal to the minimum of for I and N of A star of I. And in that case, that'll be equal to -2. So what we are doing is we're looking at these two sets. Right? If we have, because we only have 2 stations, but if we have 10 stations, we will have 10 sets of H1, H2, H3, H4, H5, and so on. So we are looking at these 2 sets and we're finding the minimum. In that case, that's -2. Okay, so we got to this point. Now we have to use that C value to compute the H values without the star. So that will be equal to HI star minus C for both sets. So in our case, we have H1 of N So we're going to look at each one of these numbers. So we're going to start with 0, and we're going to subtract -2. That is 2. 1 minus 2 is -2 is 3. 2 minus -2 is 4. 3 minus -2 is 5. 4 minus -2 is 6. -1 minus -2 is 1. 0 minus -2 is 2. Then we do the same thing for H2 and we have -1 minus -2 is 1. 0 minus -2 is 2. 0 minus -2 is 2. 1 minus minus 2 is 3. 2 minus minus 2 is 4. Minus 2 minus minus 2 is 0. Minus 1 minus minus 2 is 1. So these are the two sets. And then we'll finally able to observe what will be the maximum number of items that will be held by a carrier at any point. You see, you look at the maximum of these two, maximum value between these two sets, B is going to be equal to the maximum for I and N of H I of N, and the maximum value will be 6. So that will be 6, and that will happen for I equals 1. So that's for the loading station, and carrier N equals 5. Therefore, each carrier must have sufficient capacity to accommodate 6 items. So if you were to design for this scenario, what you're saying is, if you're going to have this many carriers, each carrier should at least have the capacity to load 6 items. Because that's the maximum that you are going to observe when the system is in steady state. So at least capacity for 6 items. If you don't have that capacity, what's going to happen is when you get to this point, actually, if you have 5 and you are going to load on a carrier, you are not going to be able to, so you're going to have to hold that item. Okay, so I know this is a little bit complicated. So what I decided to do is to go through this example with you today, and we're going to go back to this on Wednesday. And on Wednesday, we're going to do a hands-on exercise in class. So we can practice this and we have a hands-on experience. So on Wednesday, we're going to go back to this and we're going to do a practice problem, and then we're going to discuss it in class. And also, we're going to talk about the exam. So Wednesday, that's the plan. Any questions? No. So I'm going to stop here and we'll talk more on Wednesday. Typically I'll post them before you come to class. Okay. At least give me that much time, because I graded everything, but now the process of putting all that information into the system is a little tedious. Yeah. So